This is Bob Capetta from the University of Illinois at Chicago, and this lesson is a Math 181 Final Exam Review Part 2. Our first question is to find the first 5 non-zero terms of the Maclaurin polynomial for 3e to the x minus 2 cosine x. We want to do this in the most reasonable manner possible, and that is going to be using our known Maclaurin series. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial forever. And if we want 3e to the x, that will require us to multiply this polynomial by 3, which will give us 3 plus 3x plus 3x squared over 2 plus 3x cubed over 6, 3 factorial, plus 3x to the 4th over 24. Let me fix that. And that is fixed. 4 factorial, 4 times 3 is 12, times 2 is 24, times 1 is 24. So that is our Taylor polynomial for 3e to the 3x. Now we need negative 2 cosine x. We'll start with cos x, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. Those are the first 5 non-zero terms. I need negative 2 cos x, but the fact of the matter is that this one ends at x to the 4th. So we really only need the first 3 terms here. So if I have negative 2 times cosine x, that's negative 2 times all of these, distributing that, negative 2 plus 2x squared over 2 factorial minus 2x to the 4th over 4 factorial. And then, yes, of course, plus 2x to the 6th over 6 factorial, but we're going to add these together, and we're only going to go up to the x to the 4th term to get the first 5 non-zero terms, 1, 2, 3, 4, 5. So we want to add these together now. We want to add 3e to the x plus negative 2 cos x. You'll notice 3 minus 2 plus 3x. 3x squared over 2 plus 2x squared over 2 will give me 5x squared over 2, plus 3x cubed over 6, plus 3x to the 4th over 24 minus 2x to the 4th over 24. So just adding these two polynomials together, this is what we get. 1 plus 3x plus 5x squared over 2 plus 3x cubed over 6 or x cubed over 2 plus x to the 4th over 24. That would give us our first 5 non-zero terms, 1, 2, 3, 4, 5, of that function. The next question is to find the interval of convergence for this, and we're going to need to use a ratio test. So we're going to need absolute value of a sub n, absolute value of a sub n plus 1, and divide those. So the absolute value of a sub n loses the sign flasher, loses negative 1 to the n plus 1. So we get absolute x minus 2 to the n over n times 7 to the n. Then we'll need absolute value of a sub n plus 1, which is x minus 2 to the n plus 1 over n plus 1 times 7 to the n plus 1. We want to divide these two. That's our strategy. So a sub n plus 1 divided by a sub n, this divided by this. And of course, we're going to invert and multiply. So taking the reciprocal of this second fraction times n times 7 to the n over x minus 2 to the n. Notice x minus 2 to the n plus 1 divided by x minus 2 to the n is just absolute x minus 2. 7 to the n over 7 to the n plus 1 just gives me a 7 downstairs. Then we have n over n plus 1. For the ratio test, we want the limit as n goes to infinity of this. And I can pull out the absolute x minus 2 over 7 since that's not changing, only the n's are changing. And the limit as n goes to infinity of n over n plus 1 is just 1. Highest power n upstairs, highest power downstairs n over n is 1. So that the value I get is absolute x minus 2 over 7. And in the ratio test, we'll have convergence as long as that is less than 1. So that's our rule. The series will converge when this limit is less than 1. So I need absolute x minus 2 over 7 to be less than 1 to find our interval of convergence. Well, if that's the case, that means absolute x minus 2 is less than 7. Negative 7 is less than x minus 2 is less than 7. Adding 2, that'll give us negative 5 less than x less than 9. So this will be part of the interval of convergence. All I have to do now, of course, is to check the endpoints. What's happening at negative 5? What's happening at 9? So we're going to plug 9 into this function. F of 9 will be the sum of negative 1 to the n plus 1, 9 minus 2 to the n over n times 7 to the n. And we'll determine whether or not that converges. Well, 9 minus 2, of course, is 7. So we have 7 to the n upstairs, 7 to the n downstairs. Those divide out. And we get negative 1 to the n plus 1 over n. This is an alternating series. Its absolute value, 1 over n, goes to 0. As n gets large, 1 over n goes to 0. Is it decreasing? Well, 1 over n plus 1 is less than 1 over n. A bigger denominator tells you that the fraction is smaller. So we have all three of those things. It alternates, the limit of the absolute values is 0, and the absolute values are decreasing. Put all that together, what does that tell me? That tells me that this converges. This is the alternating harmonic series, by the way, but it converges by the alternating series test. So 9 is in the interval of convergence. The next question is whether or not negative 5 is in the interval of convergence. So we'll plug negative 5 in here, and we'll see whether or not that function converges. So plugging in a negative 5 for x, negative 5 minus 2 to the n will give me negative 7 to the n, which is negative 1 to the n times 7 to the n. And you'll notice the 7 to the n's cancel, but you'll also notice something here with these negative 1's. Negative 1 to the n plus 1 times negative 1 to the n is negative 1 to the 2n plus 1. If the bases are the same, we add the exponents. 2n plus 1, 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. Those are all odd numbers. Negative 1 to an odd number is always negative 1. And we could pull the negative 1 out in front. And we have negative 1 times the sum of 1 over n. That is the harmonic series. That diverges. P-series, fine if you want to use that reason, but that is a divergence. So negative 5 diverges, but 9 converges. So our interval of convergence would be negative 5 less than x less equal to 9, or written in interval notation, round bracket, negative 5 to 9, square brackets. Our next question is to express this as a series and to find the interval of convergence. And this is a power series. What to recognize, it is similar to the form of a naught over 1 minus r, or first term over 1 minus the ratio. But I need this piece to be a 1 to use that geometric series model. So to turn the 2 into a 1, I'm going to need to divide the bottom by 2 and divide the top by 2. 5 divided by 2 will be 5 halves. 2 divided by 2 is 1. 3x divided by 2 will be 3x over 2. And remember, we're using our geometric model. First term over 1 minus the common ratio. First term is 5 halves, common ratio negative 3x over 2. That will, of course, work when the absolute value of the common ratio is less than 1. So again, first is 5 halves, common ratio negative 3x over 2. So let's try to write that out. First term is 5 halves, then plus 5 halves times negative 3x over 2, plus 5 halves times negative 3x over 2 squared, plus 5 halves times negative 3x over 2 cubed. So the signs will alternate. So it may be clear to see it this way. 5 halves minus 5 halves times 3x over 2 plus 5 halves times 3x over 2 squared, etc. Writing that in sigma notation, first term, 5 halves. Common ratio, negative 3x over 2. K starts at 0 because if k is 0, negative 3x over 2 to the 0 is 1, and I start at 5 halves. So that is what our series looks like in sigma notation. We want to find the interval of convergence, so the common ratio's absolute value must be less than 1. I need the absolute value of negative 3x over 2 to be less than 1. So that's what we're heading for. Absolute value of the ratio must be smaller than 1. So that means this thing is between negative 1 and positive 1. Multiplying by 2, We have negative 2 is less than negative 3x is less than 2. We want to divide by negative 3, but if you divide by negatives, you have to switch the signs. So negative 2 over negative 3 is greater than negative 3x over negative 3 is greater than 2 over negative 3. This is 2/3. That's x. That's negative 2/3. We prefer to write this from left to right. So negative 2/3 is less than x is less than 2/3. And that is our interval of convergence. And we do not need to check the endpoints. We used a geometric series model. And in a geometric series, if the common ratio equals 1 or negative 1, it diverges. So no need to check the endpoints here, whereas with the ratio test, we had to do that. Okay, next we want to prove whether or not this converges or diverges. And we're going to appeal to the kth term divergence test or nth term divergence test. We're going to look at the elements of the sequence. As a sequence, a sub k is 2 plus 3k plus 5k squared over 1000k squared. And the limit as k goes to infinity of a sub k, ignoring the lower terms, 5k squared over 1000k squared is just going to be 5 over 1000. That's what we're going to be heading to. So we get 5 over 1000 or 0.005, but that is not 0. Remember, that's our notion. For the divergence test, if it converges to a non-zero number, or if the sequence diverges, then the series has to diverge. So the sequence converges to a non-zero number. The series, diverges by the kth term divergence test. Next example is the sum as k goes from 2 to infinity of negative 1 to the k over the natural log of k. Looking at the absolute values, well, it alternates. Looking at the absolute values, the absolute value of this is 1 over log k. As k gets large, log k gets large. 1 over a large number goes to 0. So that's our second condition of the alternating series test. And our third condition is, do the absolute values decrease? Well, we'll say 1 over log k plus 1 is less than 1 over k. No, it's not. I have to fix that. So a sub k plus 1 is 1 over log k plus 1. A sub k is 1 over log k. K plus 1 is bigger than k. Natural log of k plus 1 is bigger than natural log k. So 1 over natural log k plus 1 is less than 1 over natural log k. So indeed, this is a decreasing situation. Alternates, absolute values limit is 0, absolute values decreasing. Those 3 points together tell me that this series converges by the alternating series test. And we have one more problem to look at. The sum as k goes from 1 to infinity of k plus 7 over the square root of k cubed plus 6. We're going to approach this by looking at the limit comparison test. A sub k is what we're given here as a sequence. B sub k, highest power of the top, k to the first. Highest power of the bottom, square root of k cubed. Square root of k cubed is k to the 3/2. So that's k to the 1 over k to the 3/2, which will equal 1 over k to the 1/2. That's what I'm going to compare a sub k to. So we take the limit as k goes to infinity of a sub k divided by b sub k. So limit as k goes to infinity of this first piece divided by this second piece. Division, change to multiplication, and flip. Distributing, k times k to the 1/2, k to the 3/2 plus 7k to the 1/2. And now to do this, we're going to divide the top by k to the 3/2 and divide the bottom by k to the 3/2. So k to the 3/2 divided by k to the 3/2 will be k to the 0 will be 1. K to the 1/2 divided by k to the 3/2 is k to the negative 1. That'll just give me 7 over k. Now on the bottom, k to the 3/2 is also the square root of k cubed. So I'm just going to do it that way. If I divide this whole thing by the square root of k cubed, I divide this by the square root of k cubed, I divide this by the square root of k cubed. This, of course, is 1. So what do we have? As k goes to infinity, the top is going to 1 plus 0. The bottom is going to the square root of 1 plus 0, which is 1. Now on the limit comparison test, the result needs to be a positive finite number. 1 is a positive finite number. when that happens, both series are of the same type. So you notice I'm emphasizing the fact that it is a positive finite number, more than 0, less than infinity. So both series are of the same type. What was that sequence that defined the series for b sub k? B sub k was 1 over k to the 1/2. But the sum of 1 over k to the 1/2 diverges by the p-series test. If that p is less than 1, or between 0 and 1, it's going to diverge. If it's greater than 1, it's going to converge. If it equals 1, it also diverges as a harmonic series. So this series diverges. We said both series are of the same type. So my original series, this thing, sum of k plus 7 over the square root of k cubed plus 6, also diverges by the limit comparison test. And that will conclude this lesson.